Hi, in this particular video, we are going to look at Unit 4, which is, I think, one of the most important units in environmental science because it is so connected to everything else. When you just look at these pictures on the first slide here, you can see that what we think of as these physical systems, the geology and oceanography and atmospheric science, meteorology, all of those things come together in this unit, and really those are the foundations that support life on Earth and have shaped the distribution of life on Earth and have major impacts, of course, on things like climate, biome distribution, so many different things. So while this is a fairly small unit of study, it is of critical importance. And so we're going to talk today about some of the content that you'll see on the AP exam and why it matters. So let's just dive right in. First of all, a unit overview here. This is straight out of the course exam description, which you can look at on the College Board's website. This shows you the kind of background here and the unit at a glance with some of the major ideas in here. This is a great document to look at while you are working towards the AP exam because it really shows you the specific type of content that you're going to be asked about. The biggest things here are, if we look over on this left-hand side where you see it's a big idea, one, big idea two, these are critical. These over here are the most important things to think about really all the way through the course, which is that everything's connected. In this unit, we'll look at how energy is transferred, how energy from the sun is moved from the places where there's lots of it to where there's not much, how that changes throughout the seasons, how that influences climate, weather, ocean currents, all of those kinds of things. And then, of course, the really big idea, which is the interactions between Earth systems. This is and not just Earth systems. This is also the living systems, atmospheric systems, oceanographic systems. There are so many different ways that content in this unit interacts. And in this unit as well, you'll see it's only about 10 to 15% of the exam weighting down here in the bottom left, but doesn't mean it's not important. You'll see as we go through this today, these topics that you see over on the right there in the unit at a glance are connected to literally everything else in environmental science. So while it may have a small weighting on the exam in terms of the questions you might see, an understanding of these concepts is absolutely foundational to everything else. So don't gloss over it. Take it for what it is, which is one of the most important units in the entire year. And you do have to know a bit of geography for this and some general knowledge really about where things are found on Earth. And so as we go through this today, just bear that in mind. Some of the stuff that you'll see in these notes and that you'll read about in the course notes are things that aren't necessarily part of the AP curriculum, but there's an assumption of general knowledge about some of this as well. Things like the rock cycle, things like, where on Earth do you find volcanoes and earthquakes? Those are things that you're kind of expected to have some background knowledge on, so you can practice that. So let's get straight in with 4.1. which is all about plate tectonics. So plate tectonics, I'm sure you've heard of this, but it's a relatively new theory. For centuries, people, as they've looked at these maps of the planet, have kind of scratched their heads as they've looked at the shape of South America and Africa and thought, man, it really looks like the east side of South America seems to slot right into that space on the western side of Africa. Isn't that weird? And then you look at North America and you see the same thing. And you look at some of the other continents and you wonder, well, it really looks like they were connected in some way. And the reason for that is, well, they were connected. Back in the 1960s, Alfred Wegener first developed an explanation for what was going on. And he proposed this theory of what we now call plate tectonics, or continental drift, it's sometimes called. And it's this idea that the Earth is not as solid as we always assumed it was. That when we drill holes, all we get to is rock. But we know from volcanoes and things like that, we know there's some liquid stuff down there, that it is hot as you get deeper down into the Earth's crust and below that into the mantle. And so for the AP exam, you do need to have a kind of general understanding of the structure of Earth's geological system. And so we have this core that is solid right in the middle. And then as you look down here on the right-hand side, you've then got this sort of liquid outer core. We know very little about those parts in grey that are down there. We do know a fair bit about the mantle and the lithosphere, which is the top two most portions of the Earth system. These are solid on the top, and then we've got this plastic and semi-liquid and then very much fluid components as you go deeper down. And together, these things have shaped the Earth's outer crust for billions of years, really since our planet formed. And so this theory of plate tectonics is that the outermost surface, this thin skin of crust, oceanic and continental crust, is floating on this liquid mantle. And because it's floating and the mantle is hot, you've got these warm currents, these convection currents, where heat is moving that fluid around. And because it's moving the fluid around, it also drags the crust all over the Earth's surface. You know, you may have heard of Pangaea, which is this supercontinent that we think was formed a long, long time ago, millions of years ago, back on Earth's history. But you can see Antarctica is way down there at the bottom in this picture here. And these pieces of crust have moved around the planet for its entire history. And actually, there's evidence as you look down deep into the rocks of Antarctica that we think it used to be a rainforest. How is that possible? Right now, it's covered in ice, but that's because of its position relative to our spin around the sun, which we'll talk about in a few minutes. But Antarctica never used to be in that spot. It used to be close to the equator. And so it used to be very, very hot and humid, and so very different life forms in there. And that's what we're going to talk about today. So let's watch a brief video here, which hopefully will work. Yeah, here we go. That will show you just a good visualization of how this happened.
225 million years ago, our planet looked very different. All the continents were joined together in a single supercontinent called Pangaea. As the plates moved, this supercontinent broke up. New oceans formed as continents drifted around the globe. It's this that has created the shape of the world we know today. But the plates never stop moving. In the distant future, our continents will once again be reunited in a new giant supercontinent.
So that's important because what you learned on previous units about biodiversity and biomes and biogeography, the distribution of life around our planet, what we see today, this picture of the map you can see at the top right here of the screen, is temporary. It's just a snapshot of where things are right now, where the continents are and where the different biomes are located. As those continents move around and shift position relative to the Earth's tilt and the seasonal changes of sunlight that we see and ocean currents, all of that can change and will change. And so what is currently a rainforest, it may not be 100 million years from now. So let's get a look at how this works real brief. You don't need to know too many graphic details, just the general ideas of how this new crust is formed, how it moves. And so where new crust comes from is actually shown down in this diagram at the bottom here. This region right here is the area that we call a divergent plate boundary, where you've got new crust being formed. You look at that convection cell and the rising magma below it, you can see this hot yellow plume of molten magma forcing up to the surface. And as it breaks its way through this crack in the crust, it cools, forms new rock, but then fresh magma comes up again, and it just keeps pushing apart these layers of rock that it's creating. So it creates these two plates, right? One on the left, one on the right, and they keep getting pushed apart. These typically occur in the middle of the ocean. They're called oceanic ridges, and there's one in the middle of the Atlantic. If you look at the map on the top right of this screen here, you can see this big pale blue line that goes right the way through the Atlantic. Notice you've got the Americas on the left and Africa and Europe on the right. See how the shape of that boundary, that plate boundary where the new magma is being forced up, it follows almost like a jigsaw puzzle piece the shape of North America and South America and Africa and Europe. And so you can see that what was forcing apart these continents was happening along this line in the middle there that is shaped exactly the same. And if you were to just zip backwards in time, you would see South America, North America, Africa, and Europe coming closer and closer and closer together until they were connected. So that's what's going on, and it creates these areas of crust, We have got continental crust, which you and I are on right now. That is the land-based stuff. It tends to be less dense, so that means it's thicker, right? It's got less material compressed into it. It's less dense, and so it tends to be floating high, if you like. If you can imagine this sort of liquid system where it's floating on the mantle, sorry, on the magma. It's floating high in the water, if you want to think of it that way. Whereas oceanic crust is more dense. And so this stuff, it tends to be thinner, but much more dense. So when these two kinds of plates meet, what tends to happen is the more dense oceanic plates get forced underneath the less dense continental plates. So we're going to look at that in a moment, but you can see in the diagram at the bottom right here, the one I already circled is a divergent plate boundary where you've got fresh magma coming up and pushing apart. That's what divergent means, these plates. And then you have got some hot spots over here. These aren't really plate boundaries. They're just weaknesses in the middle of an oceanic crust, like Hawaii, where you have just a little fracture in the crust. It's not a divergent boundary. There's not really a new plate being formed there. You've just got what we call a hot spot, where there's a plume of magma coming up and it's found its way to the surface, and you get these pop-up volcanoes. But notice that oceanic plate is moving to the right. So you get an old volcano over here to the right. That's one of the first ones that was formed. And then it got pushed over to the right. And then another one popped up here, and then another one. And now here is the current active volcano. But over time, that's going to move over the hot spot, over to the right and away from it, and a new volcano will pop up. But where we really see some very dynamic tectonic phenomena is where plates collide. And that's being shown down here at the right-hand side. This is a convergent plate boundary, which we sometimes call a subduction zone down at the bottom here because of what's going on. You can see the continental plate is being pushed and forced underneath, sorry, I think I might have said that wrong. The oceanic plate, the oceanic crust is being forced down and underneath that continental plate right there. And when that happens, you see all kinds of crazy things happening. You get earthquakes because of the friction between those two plates. You can see this new continental crust is being formed as this oceanic crust melts down here. It gets incorporated into this magma, which then finds its way up through this fractured plate where you've got earthquakes and all kinds of cracks happening. And so you get these volcanoes popping up as well, where the pressure is relieved from all this extra molten rock. We're going to watch a video now that kind of shows how this works.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart. And it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption. The remarkable cycle is complete.
So you got a hint there at how connected the content in this unit is to other units. There was a reference at the end there to carbon dioxide, which you don't need to know much about at the moment, but when we come to look at Unit 9, which is global change, the greenhouse effect, climate change, things like that, that carbon dioxide gas becomes very important later on. So hold that thought. You're going to have to do a lot of that in this course, where things you've learned in each unit, you can't just memorize that and move on. You have to connect those things. That's really what this exam is all about. So just a reminder of what you saw in the video here, you can see the three categories of plate boundary or plate margins. We've got our divergent boundaries over on the left here. This tends to be oceanic, where you have new oceanic crust formed in the middle of the ocean, like the mid-Atlantic ridge. This is what's really driving everything else, because this is where new crust is formed, which pushes plates apart. Where those plates converge, where they meet together, you get these subduction zones happening, where a lot of friction, a lot of earthquakes, a lot of volcanoes popping up, and you get these trenches, these deep, deep, deep oceanic trenches, like around the Ring of Fire, which is that area around the coastline of the Pacific Ocean, which is tectonically extremely active. It is the most active zone on our planet for tectonic interactions and phenomena. So many earthquakes and volcanoes there, because you've got all this subduction going on, pressure and friction interacting. And then, of course, you have these transform faults. We know one of these very well, right? The San Andreas fault is a small, it's really a microplate, I guess you could say. It's a small transform fracture where you've got two pieces of crust sliding past each other horizontally. It's not the ones going up and over the other or underneath. It's not that they're being pulled apart, they're just sliding past each other. And so you don't get volcanoes typically here, but you do get earthquakes because there's friction. And so earthquakes, again, are a phenomenon that you have to have some knowledge of about what causes them, same with volcanoes, but you don't need to know a ton of details about them. However, you do need to know that earthquake magnitude is a logarithmic scale. So look at the graph on the right here. You can see we used to call this the Richter scale. You don't hear that word very often because there are many different ways to measure earthquake magnitude, but they are typically logarithmic. So as you look at the axis there, the y-axis, you can see it's a very odd one, right? You can see that the intervals, the increments between those numbers are not equal. Look at 8 and 9, and then 7, 6, 5, 4 isn't even on there, and then, oh yeah, there it is on the right. And then you've got 2 and 1. See how compressed that is? That's because this is a logarithmic scale. So that means that an earthquake that has a magnitude of 9, so like this one over here, it has 10 times more energy in it than one that is a magnitude 8. And that's got 10 times more than one that is a magnitude 7. So it's not like a linear scale where there's a straight line. You can see it's exponential. Look at the shape of this graph. It's showing you this, so, you know, 7.3 versus 7.6 doesn't sound like much of a difference, but it really is, because these numbers are logarithms. Same with the pH scale, same with the decibel scale with noise pollution, and same with serial dilutions when we're talking about concentrations of toxicants later on. You're going to see these logarithmic scales a lot. So this is the first one you'll probably be introduced to over this course, but it's not the last one. Just remember, just like the pH scale, it is logarithmic. Let's move on and talk about 4.2. We've not got very far. I probably need to speed up a little bit here. 4.2 is about soil. So obviously the Earth's crust, the lithosphere, is the part that we interact with the most. That's where volcanoes, earthquakes happen. It's where sediments form new rocks. It's where the rock cycle is occurring. All of that's very dynamic and affects life on Earth. But the part that really affects us most directly is this even thinner skin across the top of the Earth's crust, which is soil on land. Soil is essential to life. Without soil, you can't really have life. You maybe have some bacteria and some fungi that can cling to those particles. But soil is a dynamic, and some would argue, living thing. Because in order to be categorized as a soil, the sediments and minerals that we think of as dirt have to have this organic matter. If you look at the pie chart down at the bottom there, and you see all kinds of graphs on the AP exam, including the one we just saw, which was the logarithm one. Here we've got this circular chart, or a circle graph or pie chart showing percentages. If all you've got is a pile of gravel or sand, then you've got mineral matter, there'll be some water and some air in that, but that's not a soil. For it to be considered a soil, you have to have this stuff down here. Whoops, organic matter. So organic matter is the dead and not dead material that is in the soil. And it is something that's critical, right? That's where many of the nutrients come from that support plant life. They come from that organic matter. And it can take thousands of years for this to happen through the process of ecological succession, which you may or may not have looked at yet. If you think about when a glacier retreats, obviously the world is changing. Glaciers are retreating all over our planet. They expose rocks and these just piles of debris, ground up gravel and sand. But there's not really any living things in there yet, and these particles are quite large in size. It takes a long time to convert that gravel into soil because you need this constant repeated cycles of weathering and erosion and deposition. And then you need some of those early successional organisms, the lichens, the fungi, the bacteria to go to work. So you've got some chemical and physical weathering happening. You've got some movement, you've got deposition, particles coming in, particles leaving. And then you've got the growth of these little early successional living communities. And then they die and they decay, and their material gets incorporated into this pile of stuff that we ultimately call soil. So life is essential to this. So you can't have life without soil, and you need life to form soil. So it's this sort of chicken and egg scenario where there really has to be both. But it begins with fungi, bacteria, lichens, and then some of these little tiny early soil invertebrates, the soil mites, and little insects that live in the soil. And so what they do is they go to work on taking the material that's at the surface, moving it further down into the soil. And as they do that, and as they burrow down and create spaces, they're aerating that soil, allowing gases to be exchanged. They provide drainage channels for water, and then that cycle goes on and on and on. So as you look at the top right here, this is a really kind of cool diagram that shows you what's going on in all soils all of the time. Obviously, you've got your parent material down here at the bottom, and stuff can be lost out of the bottom here, especially if it's liquid. It can drain through and go down into the parent rock. But you can get additions as well as you get movement through earthquakes, through just deformation of rocks. You can get movement of material coming up. You get a lot of transformations going on. Chemical and physical transformations are happening in the soil. You've got additions at the surface. Obviously, that makes the most sense to us, where you've got sediments coming in from erosion, transportation and sedimentation from elsewhere. You've got dead plant and animal material now being added as well. That stuff gets incorporated down, it gets moved. We call that a translocation, showing on this arrow. And then you've got losses, right? You have erosion, but not just erosion, you just got movement, right? Stuff slides down the hill over time. It gets transported when it rains, moved across the top of the surface. So it's very, very dynamic, and all of this is happening really all of the time in a soil. You're going to learn a lot more about soil when we look at agriculture. And so some teachers, your teacher might choose to teach this particular subunit when it's relevant to do so in agriculture. But it's part of the College Board's Unit 4, so we're going to talk about it here. But just know that, again, because soil is essential to life, you're going to be hearing about it a lot as we go through this course. So when we talk about succession, which is this change in plant communities over time, which is sort of shown over on the bottom right here, you start with exposed rock. So here we've got over here on the bottom right, this is a retreating glacier, or maybe it's a volcano, or a landslide, or an earthquake, or some epic sedimentation event that's happened from a flood. And so you've got bare rock. There's no soil yet because we don't have those living things, the plant roots and things like that going down into it. Then you get your initial fungi and lichens start to break down biologically, chemically, and physical weathering happens. And you get mosses starting to grow as well. They die, and you get these cycles of growth, decay, weathering, erosion, all of that stuff happens. And that creates this really thin layer, this lens is what we call it, of soil on the top, where you do have the things we saw in this previous diagram down in the graph at the bottom, where you've got your mineral content, obviously, but you've also got air and water, and now some organic matter being incorporated in. And then eventually you get larger plants forming because they can put roots down into this soil, right? You've got to have soil for plant roots. And so the deeper and older the soil gets, the larger the plant organisms that can grow there, and the deeper the roots can penetrate. And so it just grows and grows and grows until you get this thick, rich soil shown down here in the bottom right, a mature soil at the end of this successional event. On the top right, we've got a diagram of what's known as a soil profile, and it's showing you these layers, which are known as horizons. Because if you can imagine them, they go on horizontally for miles in some cases. And so in the order in which they appear from the surface downward. This is not the sequence in which they are formed necessarily, but it is the vertical sequence from top to bottom. On the very top, you typically have what's called an O horizon, and the O stands for organic, because that's where the organic matter is. This is where the highest concentration of dead stuff is. The old leaves, the poop, the dead organisms, all of that stuff is in that. We sometimes include the leaf litter on the surface. You think about walking through a forest or something like that, where you've got that thin, loose layer of just stuff that's decaying. Loads of detritivores live there. Those are the critters that feed on that stuff. And they incorporate that down into the soil as they burrow down. And so that generates what's called an A horizon. This is the topsoil, is what we call that. Topsoil is critical to agriculture and engineering as well, because this is where you've got all kinds of chemistry going on. And it's also where, of course, the nutrients are found for a farmer's crop. So that's where the roots will penetrate into the topsoil, the A horizon. So it's your mineral matter with a large degree of organic matter as well. And we call that stuff humus. You'll see it written right here. It's kind of small, but that word humus, not to be confused with hummus, a delicious dip from the Middle East. Humus is this sticky, dark, organic matter that is the sort of nutrient-rich debris of decay. And that's what goes down into the soil. So it tends to make the A horizon darker, certainly makes the O horizon dark, sometimes even black. Then you might have what's called the E horizon under that. And you only see this in very, very mature ancient soils, because E stands for eluviation, which means leaching. It's spelled differently, but if you think of what a leech does, it sucks blood. That's what's going on here. You've got leaching. If you think about brewing some coffee, where you put your grounds into the coffee pot at the top, it's in the basket, that's like the A horizon. And then you add your water to the top, and the hot water goes through. And as it goes down through that soil, which is your coffee, the topsoil, coffee grounds, it starts to leach material, right? It starts to suck out all the good stuff that you want. And then down it goes as it percolates through and gets captured down below in your carafe, right? The coffee pot underneath. That's kind of like the B horizon, which is your subsoil. That's where the stuff moving down the soil profile tends to accumulate and end up. Notice from this diagram, there are no plant roots down there. And then it gets stuck, right? Because you've got this C horizon, which is just your parent material, really. And there's nowhere else for that material to go. So as your stuff goes downwards through here, it moves through the E horizon if it's there, and then it accumulates here in the B horizon, which is the zone of accumulation. So the E and the B horizon, we really don't talk about a whole lot in AP Environmental Science, because while major engineering projects might need to know the structure of what's going down there, and certainly that's where groundwater can move through, but for agriculture and for life at the surface, the E and the B horizon have very little impact on the surface. Now that doesn't mean that the surface can't have a big impact on the E, B, and C horizons, or even further, because the R horizon at the bottom is called regolith. That's your bedrock. That's the parent material usually down there. But remember, there could be layers and layers of that for hundreds of kilometers even on a continent. You could go way, way down at the earth, and there could be water collecting in aquifers down below there. And so material from the A horizon can, over maybe millions of years, find its way down through the soil profile, percolating and infiltrating down into the C and R horizons and below. Okay, so that's why I've put the kind of sequence of formation of soil, typical sequence. It doesn't always work this way, but obviously a very, very ancient mature soil may have all of these horizons present, but a young soil may not. Typically, you always start with the regolith, the R horizon, the unaltered parent material, which then your early successional communities go to work on, creating the C horizon, where you get weathering happening, the breaking up of that rock into smaller and smaller particles. And then you may get a thin lens of what is like an A horizon topsoil forming. And as that gets older, you get the layer of organic material as more and more life starts to colonize. You get that O horizon on the top starting to form. And then as that stuff starts to wash downwards beyond where the plant roots are found, you can see the development of a B horizon forming, where you've got material accumulating that plants haven't taken up. And then if it's a really old horizon, then that A horizon is getting thicker and thicker and thicker. You just get this increasing vertical distance, and the E horizon can form when you've got this alluviation, the zone of leaching, where material is just passing through. It's not accumulating, it's just moving, and then down it goes into the B horizon. So hold that thought for agriculture, and when we get to talking about cities and building materials later on, sustainable design, we're going to talk about soil again. So soil is made up of different particle sizes. So you have sand, you have silt, you have clay. Those designations are a measure of their size. And so you can see over on the right-hand side the difference between sand, silt, and clay. Sand are the larger particles. They can be up to 2 millimeters. They're definitely visible to the naked eye. Silt is much finer than that. It's this soft, powdery stuff, kind of equivalent to almost like talcum powder, if you know what that is, and a little thicker. It can feel a little bit gritty sometimes, but silt is often what you see building up it's the powdery, pale stuff you often see on the side of a creek, on the edge of a little river. Clay is the smallest particle. These are not visible, sometimes even under a regular light microscope. They're so small, they're a micrometer in size, or even a couple, maybe 100 nanometers in size. They can be very, very small. And they behave differently because of their size. And these different combinations of the relative abundance of sand, salt, and clay create the different properties that different soils have, that farmers are interested and that engineers are interested in. They're building roads or pouring foundation for a building or running a pipeline for the oil and gas industry. All of these three particles together and the relative abundance of those create very different chemical and physical properties. So one of the properties we're going to look at, obviously, is the physical property of what's called porosity. And porosity, as the name suggests, is to do with pore spaces. And so pore spaces are the gaps between the particles. So if you can imagine a pile of materials, just dirt stacked together, it's not just materials, right? There's gases in there. 25% of your soil, at least, is air. It's gases that are down in the soil. So there's space for that. Same with water, right? The water can be in the soil. The pore space is just the volume of the gaps between the particles. And perhaps counterintuitively, clay has the highest of those. Pretty strange. Clay is the smallest particle. You would think it would have the smallest pore spaces, but it doesn't. Now, the pore spaces are tiny, but they're there. So if you total up, if you look at the boxes down at the bottom here, there's the same amount of material that's in these boxes on the bottom right here. But when you look at the total pore space for clay, it will have more total pore space than any of those others. Weird. However, there's another term when we talk about soil properties, and that is permeability. And permeability it's related to porosity, but it is not the same thing. And high porosity does not always equal high permeability. We're going to watch a video in just a moment that'll show you that. Permeability it is a measure of how well connected the pore spaces are, because it really is measuring the rate that water flows through a column of that material. That is the rate of permeability. In this case, pure sand or gravel, it has the highest. The larger your particle sizes are, typically the higher the permeability it has. So let's just kind of back up a little bit here. Clay has the smallest particle sizes. It's got the most pore space because of that. However, those pore spaces are so tiny, they aren't very well connected to each other. So if you pour water into the top of a column of clay, it takes a long time for that water to flow through. But if you think about going to the beach, where you maybe have built sand castles as a kid and you dug the little moat and you filled it with water with your bucket and then you ran back to the ocean to get more water, by the time you come back to your sand castle, all of that water is gone, right? Because the pore spaces are so well connected in sand, the water flows straight through it. The high surface area of clay causes water to cling to those little tiny particles because of water's property of adhesion and cohesion, right? And so it holds on to water. So soils that have a lot of clay in them tend to have a high water holding capacity at the bottom of the screen here. And you can see that illustrated in the diagram to the right, where it takes 200 years for water to make it out of the bottom of that bucket of clay down here on the bottom right. That 200 years, 200 days for silt, maybe 2 hours for sand, maybe 2 minutes for all of that water to move through. Because gravel has very high permeability, clay has very low permeability. But as a farmer or as an engineer, you really need to know how much clay have I got, how much sand have I got, because that's going to determine how often and how much you need to irrigate your crops, or how much the water is going to stay standing at the surface if you're building a foundation or you're laying a pipeline. All of these things are critical. So let's just look at a little video here that illustrates this property of porosity and permeability.
Here's the backyard scene you're probably familiar with. You watered your plants, but where did all that water go? Let's find out by looking below the ground into the soil. Soil is made up of particles of broken down rocks. These particles have open spaces between them, which are called voids. When water is added to soil, these voids create a pathway through which the water flows. This tendency of water to flow through soil is called permeability. Soil particles can be of different sizes. Some are large, while others are small. Large particles have larger void spaces through which water can flow easily. They have high permeability. On the other hand, smaller soil particles have smaller void spaces, and thus lower permeability. This can be easily explained using a simple experiment. 3 types of soil samples are taken: gravel, sand, and clay. They are placed in funnels, and 100 milliliters of water is poured into each one. We can see that water flows quickly through gravel. This is because gravel has large soil particles and hence higher permeability. When water is added to the sand, it takes more time to flow compared to gravel. This is because sand has smaller sized particles than gravel. On the other hand, clay has the smallest soil particles among these samples, and thus the lowest permeability. Even after an hour of testing, water has hardly flowed through the clay. Permeability can be linked to many.
Okay, so this idea of soil texture is critical for agriculture, and it's another example of where you will see what we call non-traditional representations of data, where you'll be shown some scientific quantitative information, but in an unusual way. And so one of these is shown over, well, 2 of them are shown on the right-hand side, relating to soil texture and how we measure the particle sizes of soils. So there's 2 kinds of tests you can do. You've got what's called a qualitative test, where you're measuring some quality of it. It tends to be a little subjective. And we'll watch a little video that's going to show you how we do that. But you'll probably do a lab like this, where you feel it with your hands. You look to see how well does the soil hold together. Is it sticky? Is it smooth? Is it gritty and granular? And you can also do a more quantitative test, where you do what's called a sedimentation test. You put your soil in a jar and you shake it up with a whole lot of water, and then you wait for it to settle out. And you can see in this diagram over here on the right, the text is kind of small, but the larger particles, in this case gravel, they settle out of this sedimentation jar very quickly, and then you get a layer of sand above that, and then silt, and then you get clay, and it may not even settle at all when you do this. Clay can stay suspended for hours, days, weeks, or even months before it falls out of the solution. It's so small. And so you can measure, doing this, the relative abundance of these different particles. And remember, the 3 that we're most interested in are these 3. It's your clay, your silt, and your sand. Those are the 3 particle sizes that determine the soil's texture. So once you've measured the relative depth of these 3 layers, how much sand have we got from here to here? How much silt have we got here to here? How much clay have we got here to here? You measure that in millimeters, and you get your total volume, right, which is from here. Sorry, my hands are a bit shaky. From here, get that total volume, and now you can generate a percentage. And once you've got the percentage, then you can read what's called the soil texture chart, which is shown at the bottom here. And the video we're going to watch in just a moment will show you how to read that. But here we're looking at an example of a soil that's been highlighted in yellow, that is 10% clay, 20% silt, and 70% sand. This triangular chart is kind of unusual because you've got 3 sides to it. I mean, how often do you see a graph that's got 3 sides? In geometry or algebra, you might have seen one where you've got the x, y, and then the z. I'm showing you 3 dimensions, but here we've got these three lines, but they never bisect, at least with their axes, right? There's no crossing point. Clay is always on the left, silt is always on the right, sand is on the bottom, and you always start with clay because clay is really the only horizontal line you've got. You read clay from left to right as if you were reading along an x-axis. However, the axis is really going in this direction. So this soil, let's say it had 10% clay. So here's our 10% clay. You start there on the left-hand side of your chart, and then you read along this way. You can imagine drawing the line all the way across from side to side. And then from your texture test, you determined that there was 20% silt. So you find your 20% silt on this side, and you measure downwards. Often these numbers are angled to give you the clue. Down you go along the 20% line, all the way down here. And then you don't even need to measure the third one because almost like a pie chart, those percentages will add up, right? 10 and 20 is 30, so the rest, 70%, has to be sand. And if you did draw the line upwards from 70% here, you'd see there's the crossing point. And we would call that a sandy loam. So soil texture is important. The best kinds of soils are the ones that fall kind of down here on the bottom of this. These are the ones that don't have too much clay in them, because if you have a lot of clay, then as we saw from the permeability information on the previous slides, you can have very low permeability. And also you can have expansion and contraction, which can damage structures that are below ground. And farmers don't like it either because it tends to hold on to the water for too long. It doesn't let it penetrate through the soil. And so we're really interested primarily in this kind of soil. This is the best kind of farming soil, loam. Got the perfect blend. But texture isn't the only thing you need to worry about if you're a farmer or an engineer. You also need to know about the chemistry of your soil. That's the other property that matters. The pH is especially important, as you'll see in the agricultural unit. pH influences nutrient availability. And the lower the pH goes, the more some of these other minerals and even metals can become dissolved in the soil. And that changes the chemistry, obviously. The big three are what we call NPK. That's nitrogen, phosphorus, and potassium, which, although it starts with a P, chemical symbol is a K. So N, P, and K are really the big three macronutrients that farmers are interested in. You'll learn more about those later. But often when we're doing tests of soil chemistry, we're interested in those three things. And of course, those determine crop yields. So farmers are very interested in it, but so are engineers, because corrosion can happen with pipes and structures underground. The conduit pipes that contain your electrical stuff and your sewer lines, all of those can be affected by corrosion, and that's influenced by soil chemistry. So I've got a couple of quick little videos. You probably won't watch them all. You can see them if you want to by pulling up the actual notes file, but this is just showing you how we do a soil texture test by feel. That's that qualitative test. And on the right, just another example of how to read the soil triangle. So I'll probably just show this.
A farmer first needs to know a lot about their soil texture so that they know how much water it can actually hold and if they need to irrigate it or if it'll grow just based on the amount of water that they received. They need to also know the soil texture size so they know how the nutrients are and what type of amendments they might need to make into the soil to give it some more nitrogen, phosphorus, or potassium. One of the quick tools that you can do is just using this called a soil probe, and it simply lets you get a good section of the soil that you have underneath you. But I'm going to take my soil about enough to get the palm of your hand, and you'll take some water and get just enough water so you can get a nice ball. And then once you get a nice ball like this, you basically take your two fingers here and try to create a ribbon and see how far out you can get it to go. And I can tell that it's already starting to break here. So since I have about less than an inch or so of the ribbon, I know that I have probably a silty loam. If it were to go farther, I would have more of a silty clay loam, which means it would hold even more water than the amount of soil that I have right here. So when you add more water to it, then it allows you to feel for the grittiness. If it's gritty, it would be more sand. If it's really soft like this one is, it has a lot more of your clay or your silt components in there as well. Another quick, easy way that you could try to determine how much sand, silt, and clay that you have is to take some little test tubes or little clear containers and put some of the soil in it that you got from your soil sample. And then if you add some water to it and shake it up really vigorously, if you let it set a whole night, you'll be able to see it'll start to clear up, and then you know that you'll be able to determine the layers of sand, silt, and clay that you actually have. You can see at the very bottom there's the sandy layer, then we have the silty layer, and then a little bit of clay would be towards the top, and then anything kind of floating in there is your organic matter and other materials that'll help add more nutrients to the soil.
So you get the idea. Also in this unit, 4.4 now, we're switching gears. Notice all of these are to do with the sort of physical components that support life. We looked at the rocks and plate tectonics. We've looked at the outermost thin layer of that material, which is our soil. And now we're going even further upwards into the atmosphere, which of course is essential for life as well. And it's important to bear in mind with this that just like in plate tectonics and in soil formation, time changes everything. So the continents have moved around, soil forms over time. It can be thousands of years to make several inches of topsoil, and then it can move. It can be washed away, it can blow away. And the same is true of our atmosphere. The current composition that we see over on the right-hand side here, it has not always been this way. Earth's history has been really a kind of tale of tragedy of life getting established and then almost going extinct, and then getting established again and almost going extinct. And so changes in the oceans that we'll see in a minute, and then obviously with the plate tectonics and volcanic activity, meteor impacts, and then changes in the atmosphere, these have all had dramatic impacts on biodiversity on our planet. Right now, we've got a huge amount of nitrogen in our atmosphere, 78%. That is incredible. That's a vast amount. The reason there's so much of it there is because it's almost like a noble gas. It's not obviously a noble gas, but it naturally forms this molecule that has a triple covalent bond, N2. It's two atoms of nitrogen with a triple covalent bond holding them together. That makes it a very difficult bond to break, which means it doesn't really do any chemistry. So nitrogen, we use it to fill tires on cars sometimes. We use it to fill optical equipment because it doesn't react. It's kind of heavy, it doesn't escape very easily. And so nitrogen is very stable. And so as we've created more and more of it in our atmosphere, it's just built up there and has stayed there. And as you've learned from, I think, Unit 1 and 2, the only way that that gas can come back into the biosphere and go into living things is through lightning, or more commonly, nitrogen-fixing bacteria can turn that nitrogen into useful form. But then, of course, it goes back into the atmosphere and stays there. Oxygen is the next most common, thankfully. We've got a lot of that. And this is very unusual, right? To have that much oxygen in the atmosphere, because oxygen, unlike inert, is not a stable gas. It's very reactive. So you'd think there'd be hardly any of it in the atmosphere. This just goes to show that we've been building oxygen in our atmosphere for a long, long time. Hundreds and hundreds of millions of years of buildup of oxygen. So if we lost all of the plants on our planet immediately overnight, we would still have oxygen in the atmosphere for a long, long time because there is just so much of it up. Now, lots of other things would happen, but let's not go into that right now. Let's talk about the layers of our atmosphere, because it's not all the same. When we look at that graph on the top right, that is our troposphere. That's what we're talking about. That is the layer of the gas, sorry, the layer of our atmosphere, as you can see from the bottom right diagram here, that is closest to the Earth's surface. It's the air that we breathe. It's where life exists. It's where all of our weather happens. And even though it's the thinnest of all of the layers, you can see it's about 10 miles thick, it actually constitutes 75% of the atmospheric gases. So all of the matter, all of that carbon, nitrogen, oxygen, argon, carbon dioxide, all of that, 75% of that is in the troposphere. So it's thin, but it's very, very dense. It's compressed. And that makes sense if you think about it, because all these gases are falling towards the Earth due to gravity, and they're pushing down, creating air pressure, which is what you feel it when you dive down into the bottom of a pool. You feel the water pressure. Well, we're exactly the same as that. We're all wandering about on Earth's surface like lobsters at the bottom of the ocean. and there's an ocean of fluids, these gases crushing down upon us, and we can feel it. A lot of people, when they go to the top of a mountain, a very high mountain, get headaches because the pressure is so different up there, because there's less gas pushing down on you. Anyhow, let's talk about these layers, because you do need to know a little bit about this. And again, as with all units, this stuff often gets incorporated in other units as well. And in particular, 4.4 comes in later on in Unit 9 when we look at the greenhouse effect, greenhouse gases, and climate change. So for now, we're just going to do a little bit of background to the atmosphere and its history and its kind of composition and changes, and you'll learn a lot more about that later on. So these layers, you can see we've got the troposphere, then we have the stratosphere, next out is the mesosphere, then we have the thermosphere, and then some scientists consider another layer called the exosphere. That really is outer space. There are so few particles out there, just occasional molecules. It's almost a full vacuum up there, and these are particles that are just escaping out into space because they're not really held by Earth's gravity any longer. The two layers that are most important to us are the troposphere, where we breathe and our weather is, and the stratosphere, because that is where the ozone layer is. And you're going to hear a lot more about that in Unit 9 as well, the ozone layer and ozone depletion. The ozone layer was critical to life on Earth, and the reason why we have so much oxygen being found in our atmosphere presently is because all through those years of the stromatolites forming, those little weird little algae bacteria type critters that live in that ancient ocean, there are a lot of photosynthetic organisms back then. We now, they're like blue-green algae, but they're photosynthetic, and they were creating this, what was initially toxic gas that was escaping the oceans, going up into our atmosphere and just building up and building up and building up, and honestly preventing life on land until terrestrial photosynthetic organisms were able to get established. And the reason they could get established on land was because as that early oxygen went higher and higher and higher, it began interacting with ultraviolet light from the sun, and it formed this layer of ozone, which is O3. Not O2, which is oxygen, O3, a triatomic molecule of ozone. And that ozone, because of the way those bonds form and break and form and break, it absorbs large amounts of ultraviolet light. And so the formation of all that gas in Earth's ancient atmosphere started to block out the ultraviolet light, but was preventing life on land from forming. UV light disappears in the oceans and in water very quickly in the first few inches. But on land, it penetrates the cells of living organisms and it disrupts DNA. It breaks it apart, and that's why you get skin cancer from ultraviolet light. But your sunburns are formed from just 1% of the sun's ultraviolet light. Imagine what it was like if you were getting 100 times that. That's why life really couldn't exist on land until that ozone layer started to appear. And now we have photosynthetic organisms on land that suck that oxygen back out of the atmosphere, and on it goes. And who knows, a million years from now, who knows what the atmosphere will look like. But these layers are defined by their composition of gases, by their density, and also primarily by the changes in temperature that occur. This is where things can get a bit weird. Because as you look at this graph over on the bottom right here we are down in the troposphere. Earth's surface is right at the bottom of this x-axis. We've got altitude in kilometers and in miles. And then we've got temperature in Celsius along the bottom. Pressure is shown over here as like a little extension to this graph. Air pressure, which is like, you can think of it like the weight of gases crushing down on you. Let's just look at the pressure. You can see it decreases as you go higher and higher, further up into our atmosphere. There's less and less pressure. And you intuitively know that the higher up you go a mountain, the colder and colder it gets. And that's true all the way to this boundary layer called the tropopause. And you may have seen this layer. If you've ever flown on an aircraft that's gone a long distance, it often goes out from the troposphere through the tropopause into the troposphere. And you can see with these massive thunderstorms that form, like this thing down here, you can see these sort of what we call an anvil top. And the top of that anvil is often the top of the troposphere. You can go above that in an airplane. But notice what happens to the yellow line. This line that is representing temperature, it was decreasing as we were going up higher and higher in the troposphere. But look at what happens now. Now the temperature decreases the higher we go up. Sorry, it increases the higher we go in the stratosphere. What's going on here? You'd think the further away you get from Earth's surface, the colder it would get because of the convection of that heat and the radiation from the Earth's surface. You'd think it would get colder. Why doesn't it get colder as you go higher in the stratosphere? Why does it get warmer? It's again because of that ozone layer, that the interaction with UV light generates heat. And then you go up into the stratosphere further up, and you hit the top of it, which is the stratopause, which is this line that delineates the mesosphere division from the stratosphere. And it's not like you can really see these lines. They're fairly arbitrary and they can shift. But they do represent a change in direction of the temperature as you go up in altitude. And so here in the mesosphere, once again, temperature starts to decrease. This is where meteors tend to burn up in here. And then you go even higher, you go into what's called the thermosphere. And this is where things get a bit weird. And really our definition of temperature breaks down completely, because you put a thermometer up here, it's basically going to measure nothing at all. It's going to be zero. It's going to be very, very cold. But then occasionally you'll get these massive temporary spikes as a particle hits that thermometer. Because remember, thermometers measure thermal energy in the form of kinetic energy, right? Particles hitting things at velocity. Particles in the thermosphere are moving so quickly, they technically have a lot of kinetic energy, which means they got a lot of thermal energy. But we don't need to worry about that. The only thing you need to know about the thermosphere is that really this is where the aurora borealis is happening, because you've got this interaction between Earth's outermost layer and the ionizing radiation from the sun that's coming in the solar wind. And that leads to our atmosphere literally burning up, especially at the poles, where the magnetic force field around us, the magnetic shield, is at its weakest. You see the atmosphere on fire. And so as beautiful as it looks, the northern lights, the aurora borealis, I don't think they're very beautiful. That's a scary thought, that that's our atmosphere on fire. And if we had no magnetic shield around us, we'd see that everywhere on Earth's planet. And that's a scary thought. Anyway, let's get a look here at this next part of the atmospheric component of our Earth systems and resources unit. Gases are just like liquids, they are fluids, which means they can move by convection. Solids don't, right? It's conduction that happens. We just talked about that kinetic theory of energy where you've got particle movement. Conduction is the sort of vibration, but the particles can't move past each other. In liquids and in gases, so in our atmosphere and in the oceans and in lakes and rivers, those particles can move when they get more kinetic energy. They can flow past each other, so you get convection forming. So if you think about our planet, where is it always hot? The equator, right? That is where sunlight is at its strongest. We get the most what we call insolation at the equator, in those tropics between 30 degrees north and 30 degrees south. This diagram you're looking at on the right-hand side, you see the equator down on the bottom right there? That's that dotted yellow line. 30 degrees north is in the northern hemisphere. That's that's the boundary of the northern tropics. But you can imagine if you go 30 degrees south, there's another area down there that's exactly the same. And so what happens is you get this heat is generated from sunlight striking the Earth's surface and the ocean surface at the equator, and it's constant, right? 12 hours every single day, 365 days a year. It is hot, hot, hot in the equator. So that hot air rises, and it's always rising. It gets less dense, right? You've got expansion due to the higher kinetic energy. It picks up more volume, and it moves upwards in the atmosphere. You get rising hot air. But wait a second, does that mean if you live on the equator that you suffocate because all your air is rising away from you? Not at all, right? We get wind that pulls in cooler air from other parts of the Earth's surface, and it literally draws it towards the equator, because it's that's where you've got high pressure. You've got this rising air, and you know how nature abhors a vacuum. You get air then getting pulled in from where it's been sinking. So just look at this picture that we've got down at the bottom right here. You can see at the equator is this zone here. We've got rising hot air. But then in the northern hemisphere, that air gets pulled to the north. The same thing happens down here in the south. We just don't see it on this diagram. In the northern hemisphere, you've got this hot air rising and getting dragged towards the poles. But remember, in the troposphere, as you go higher and higher, what happens to the temperature? It gets colder. So now it's cooling, and what does cold air do? Well, it sinks. So as this hot air rises, well, now it gradually cools, and down it goes. And so now you've got this sinking cooler air. that falls to the surface and it gets pulled back to where it came, right back to the equator. And that's what wind is. And so all the way around 30 degrees north, this tropical zone around the equator and northwards and southwards, you've got this zone where all the dominant prevailing winds are being pulled towards the equator. And then up they go and round they go again. We call those convection cells. And the first one, closest to the equator, are the Hadley cells, one that's north and one that's south. And then you've got another convection cell. Look at this one here, the Ferrel cell. This one is where you've got sinking air that came from the tropics. Down it goes. Well, now it's getting pulled, some of that gets pulled northwards because you've got another zone here of rising air, where up comes the air. This time it's getting dragged down back towards this area of sinking air, right? That's what happens. So down it goes, it's cold, it sinks down towards the surface and gets pulled towards 60 degrees. There's another circulation system called the Ferrel cell. And then around the poles, north and south, you have the polar cells as well. One thing to remember about this is that winds always blow from areas of high pressure, where the air is sinking towards the earth and it's building up pressure. That wind, that air gets moved to the areas where there's low pressure, where the air is rising. And that's happening all around the planet. So these cells, you can think of them as like donuts around the earth that have been there ever since we had an atmosphere. Now the tectonic plates have moved underneath these cells, and that's how you could have a rainforest in Antarctica millions of years ago, because maybe Antarctica used to be right here for a while, sitting right on the equator underneath those Hadley cells, getting a lot of rainfall and heat, and then it moved, right? Down it went, south and off the screen where it is currently. So let's just watch a brief video, I think, that's going to show us a little bit more detail about how this all works, the three cells.
The last video showed that different parts of the Earth heat up differently, with the equator receiving more radiative heat from the sun than the poles. And the purpose of global circulation is to redistribute this heat. If the Earth did not rotate and was a simple landmass with no oceans, we would have a single circulatory cell in each hemisphere, where hotter air would rise at the equator and flow toward the poles. The air would sink as it cools and then return towards the equator. But the unequal distribution of land and ocean and the speed of the Earth's rotation make this circulation system more complicated, giving us a three-cell pattern which exists in both the northern and southern hemispheres. The largest cells are the Hadley cells. At the equator, the warmer, less dense air rises. It rises to a height of about 18 kilometers and spreads out underneath the tropopause. The tropopause acts as a lid to the lowest part of our atmosphere, which contains all of our weather. The warm air spreads out towards the poles, gradually cooling and sinking as it moves, before descending to the surface and flowing back to the equator. The smallest cells are the polar cells. Cold, dense air descending in the polar regions flows at low levels to about 60 to 70 degrees north or south. As the air leaves the polar regions, it starts to warm and rise, returning to the poles at high levels. Between the Hadley and polar cells are the Ferrel cells. Unlike the other cells, the Ferrel cells are not driven by temperature. These cells flow in the opposite direction to the Hadley and polar cells, acting like a gear. These circulating cells not only transport heat from the equator to the poles, but also result in semi-permanent areas of high and low pressure due to the rising and descending parts of the circulation cells, giving us our climatic zones.
So, we saw a little bit about that when you looked at the biomes earlier on in other units, and their distribution around the planet is largely caused by the presence of these circulatory cells, these convection cells, like the Hadley and the Ferrel cells and the polar cells. Now, as you saw in that video, and as is illustrated down here on the bottom right in this diagram, when you look at the cells themselves, down here, let's just look at that one cell, you'll see that, just like on the video, the rising air, it gets up, pulled up into the atmosphere at the equator and goes towards, in this case, we're looking at the one going towards 30 degrees north, where it hits the surface, it's cooler air, and it gets dragged backwards to the equator in a straight line. However, that is not, in experience and in reality, how those winds move back to the equator. They are experienced at Earth's surface as curved winds. You see those arrows down there? Look at the curves blowing towards the equator, but not in a straight line like they are in the Hadley cells. It looks like a straight line, right? But what's going on here? Why is it a curved line? Well, there's a couple of things going on here. First of all, our planet spins counterclockwise, right? So that's in the opposite direction to the clock. So it's round like that. Terrible circle. You get the idea. That's the direction it goes, all right? So notice the arrow here. It's showing you the direction of our rotation, spinning counterclockwise around our axis. So imagine if you were standing at the North Pole and you wanted to throw a ball to somebody standing down there on the tip of Brazil. You could throw your ball and the expected path would be a straight line, right? You're spinning, so is the person standing in Brazil. But the problem is, think about when you used to play on a merry-go-round, right? If you ever did that as a kid. It was scary to be standing on the edge of a merry-go-round, right? It's so fast, you could feel the G-force, you have to cling on, you get thrown off if you're not careful. The safest place to be was right in the middle because you really didn't feel any G-forces at all. That's because you're rotating a much smaller distance in the middle than you are standing on the edge of the merry-go-round. So if you're standing on the equator here, you're moving a much greater distance in the same amount of time as somebody standing on the North Pole, which means, therefore, that your velocity is much, much higher. So you can throw the ball from the North Pole and it will travel at that velocity that you throw it at, but by the time it reaches your intended target, your target's moved, right? That person standing on the tip of Brazil is now somewhere, well, where would they be? The equivalent would be over probably somewhere in West Africa now, and your ball, it may land, over there, but it's not. It will not hit the target. And this is something called the Coriolis effect, and it's what generates this. Notice these curved patterns here, where you've got a diagram going this direction here, and then above 30 degrees north, it's going this way. And you see what that does? It sets up this rotation, like this shearing of high and low pressure winds that rotate round, creating these hurricanes that spin counterclockwise in the northern hemisphere. But then the same thing's happening down here, but now you've got it spinning in the clockwise direction. Sorry, yes, the clockwise direction, all the way around. In the, I'm drawing in the wrong place here. Here we go. In the southern hemisphere, they spin in this direction, clockwise, and call them typhoons. So let's just watch a quick video that really illustrates a difficult concept. The Coriolis effect is one that a lot of students get very confused by, and I think this is the best video I've ever seen that just illustrates how it works.
Picture a circle. Here's its center, here's point A, and here's point B. Point A is twice the distance from the center of the circle than point B. Oh yeah, and it spins from its center. In 2 seconds, both points do one full revolution. But to go all the way around, point A has to go this far, while point B only has to go this far. And we all know if something travels a greater distance in a shorter amount of time, it must be going faster. So point A must be moving faster than point B. Okay, now swap out this flat circle for the Earth, and the same thing is true. All points closer to the center, say like someone in Greenland, will be spinning slower when compared to points spinning further away from it, say like people in Brazil, closer to the equator. So if we look at it all flattened out, we can picture something like this. Arrows at the equator travel faster than arrows at the 45-degree line, like we just observed. Now imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north, where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you, but if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind. And the same things for the southern hemisphere. Moving towards the equator always results in falling behind, while moving away results in pushing ahead. Okay, now imagine a low-pressure cell. That means all the air around it will get sucked into the center. But the air coming from the equator will be traveling faster, so it will deflect to the right, while the air coming from the poles will be moving slower, so they'll fall behind and deflect to the left. What this results in is a circular air current spinning counterclockwise, and that's exactly what hurricanes are, low-pressure cells spinning because of the Coriolis effect. Moving this example down to the southern hemisphere, things are reversed. A low-pressure cell will still suck in the surrounding air, but now the air coming from above will be moving faster, again deflecting to the right, while the air coming from below is moving slower, again falling behind by moving to the left. This results in a clockwise spin, which is why storms in the southern hemisphere spin this way. And that's about it. It's a short video, and that's kind of the point. I hope you got what you came for.
So, good visualization of a very difficult concept. But of course, it's critical to life on Earth because those atmospheric patterns have been continuing for hundreds of millions of years and will continue to do that no matter where the continents are underneath, shaping the climate and the weather as well. So let's move on to another, really, I guess you could call this a geological and hydrological feature of Earth's systems and resources, and that's 4.6 watersheds. It's a very small part of this unit, but it's a very big concept that will become very important when you get to Unit 8, which is when you look at things like terrestrial pollution and water pollution, because it's a very useful term or concept to use when describing geographical areas, the concept of a watershed. And so what a watershed is an area of land that separates one river basin from another. So if you look at the picture on the top right, you'll see there is a dotted white line around the outside of this terrestrial area. That is the watershed of the river that you see in the middle. That's all feeding into this lake or the ocean or whatever that is that's there at the bottom. So if it rains outside of that dotted line, then that precipitation, that rainfall, will go into a different watershed. So we call it a divide. We've got one in the United States, the Continental Divide, which runs up kind of through the Rockies, which is where if you're on the eastern side of that divide, that means if it rains there, all of your water will eventually find its way. If it doesn't go into groundwater, it'll eventually go into the Atlantic Ocean. But if you step onto the other side of that line, the other side of that divide, onto the western side, well, now if it rains right there, all of that rainfall will find its way into the Pacific Ocean. So we call it the Continental Divide, but every river has its own divide, its own watershed. So it's a very useful unit of land measurement and a good concept to use, especially when you're thinking about land use and pollution. Because if you imagine, let's say you find some really nasty pollution down here, right here at the mouth of this river. Well, where did it come from? Well, the only things we can conclude for sure is that, well, it didn't come from over here, right? It couldn't have come from outside or over here or over there. It didn't come from any of those places, but it could have come from anywhere inside this line, because that is the boundary of the watershed. So let's say there's a factory over here. Well, could that have done it? Maybe. What if there is a farm over here? Could that have done it? Could have done, because it's all within the watershed. It's always good to have that kind of big picture in mind when you're thinking about water pollution, when you're thinking about soil, when you're thinking about erosion and land use and sedimentation and precipitation and the hydrological cycle. All of those things are very useful to connect them to this concept of a watershed. You often have, for major rivers, you have these watershed management groups. They're often non-profit organizations that are interested in the whole river system, because look at the picture on the bottom right. You maybe already know what that represents. So that is the watershed of the Mississippi River. Every single line on there is a tributary. So it's you see the tributaries over here. This is a tributary. There's one here and here, and there's another one there, another one there, another one there, another one here. All of those are tributaries of this big river right here. That is the main river for which it has a watershed, and it has multiple tributaries that feed into it. Here's the Mississippi River exiting down here in New Orleans. But look at where that water has come from. Look at the watershed for the Mississippi River. It is enormous. And think of the different land uses that are happening here. You've got industry, especially this is the industrial heartland of our country. And then you've got all these agricultural areas over here as well, the Midwest, the farmland and ranch and rangeland. So you've got all kinds of land use going on. So if we find pollution down here at New Orleans, where did it come from? Boy, could it come from anywhere in there. So when we look when you go to the next unit, the land and water use and land management, these watershed management groups, they often have to transcend state boundaries. Because, yeah, you couldn't very easily blame Texas for pollution down there. You certainly couldn't blame Florida, right, for any pollution that's in the Mississippi River. But there's a lot of other states that are in this whole region that have their own laws, their own regulations, their own rules of land management. So you often have to have a big picture approach to manage these river basins or watersheds. So let's kind of close the loop here and talk about these big picture patterns of Earth's global climate, things that have influenced life on Earth over the hundreds of millions of years that life has been on our planet, and will do into the future. Many of these things are very cyclical and predictable. And so we're going to look at how the seasons that just seem to come and go year after year, it's the same, spring, summer, fall, and then winter, but we don't experience them in the same way in every place on Earth. I was told, I mean, I'm from Scotland, and that's where I came from to come to America. And Scotland is, it's way over here on this little map. I'm up north, way up there. Whereas now I'm down in Houston, which it's hard to see on here, but it's right about here, right? It's up there. So there's a big difference in latitude. And I was told when I moved from Scotland to Houston by some people that lived there that I could experience 4 seasons, and I should expect 4 seasons, and most summers would be early summer, summer, late summer, and not summer. And I can conclude that, yes, they were correct. It is basically hot down here, and then you get this cooler winter that's glorious. So, but why is that? What's driving that? Well, there's a few different things that are geological and atmospheric to some extent, but they're also solar, right? They're to do with the astronomy of our planet. So let's get a look at this picture on the top right. Rays from the sun, you can imagine them being these parallel lines of radiation from the sun. They strike at a straight line, right? They're not coming in at an angle, they come straight to our planet. And this is a bit misleading when you look at the picture on the bottom right. If this really was the size of our planet, the blue circle there, then the sun would be the size of my entire house, maybe more, right? It is enormous. And so these lines of radiation that come from the sun are these straight lines. Imagine them like sunbeams, like you used to draw as a kid in the corner of your picture coming out of the sun. So here on the top right, we've got these straight lines coming in. But notice what happens. At the equator, that sun's ray, represented by bar A, it hits an area of the surface. You can imagine this kind of relatively square dotted line at the surface on the equator. It's quite small. Now look at ray B, and you can see that the area of land where that ray is striking is a bit larger. But look at ray C, up close to the Arctic Circle there. I mean, look how big this region is right here. It's a much larger area, but it's the same amount of energy striking it. So what that means is that the amount of energy per square meter is going to be a lot smaller here at point C than it is at point A, where you've got the same amount of energy that's striking a much smaller region of the Earth's surface. So it's more concentrated when it hits. That means you get more heat generated in A than you do in area C. That's why it's colder in Scotland than it is in Houston, because there's just the same amount of sunlight is striking a much larger curved area of Earth's surface as it hits. But that's not the end of the story. If our planet wasn't tilted, then we would not experience any seasons. Scotland would just be basically cold all year round, and Houston would be basically hot all year round. But our planet is tilted, and the tilt is about 23 degrees from vertical, as shown in the diagram below. And as we move around the sun, the tilt stays the same. It doesn't flip backwards and forwards. It stays exactly like that. And so what we're seeing in the diagram on the bottom right here is June on the left, and then December on the right. And so you'll notice, because the tilt is still the same, we've now got a situation where in June on the left, the northern hemisphere, those areas north of the equator, are experiencing a lot more of that direct sunlight where it's concentrated on a smaller area of land. It's almost like that the tropical area between the equator and 30 degrees north is being angled towards the sun more. So it's getting a lot more energy than areas that are south of the equator. Even though we're spinning, we're all getting some sunlight, right? We still get the same number of hours of the day of sunlight and things going around, But because we're tilted towards it, actually, it's not entirely accurate. The daylight hours do change north and south, right? Which is why, like in Scotland, it would be dark in the winter at about 4 o'clock in Aberdeen. And then, the sun wouldn't come up until much later in the morning. You'd have just a much smaller days of sunlight. But then in the summer, it would flip, and it would be still sunny at midnight. Crazy. Anywho, you can see what's going on the bottom right-hand side here. So June on the left is our summer, where I am in Houston. If you live in the northern hemisphere, that's summertime for us, because the tilt of the Earth has angled us more directly towards the sun. So we get more insolation of sunlight, so it's hotter. Southern hemisphere, notice as you look at that diagram on the bottom right, it's more tilted away, so they get fewer hours of daylight and less sunlight as a result of that, and less heat, so it's colder. It's their winter. But then you flip over to the right-hand side, December 22nd. Well, now the opposite has happened. We're now tilted in the northern hemisphere away from the sun. So we get less of that sunlight. It is colder, the days are shorter, and it's our winter, but it's summertime in Australia. Christmas Day in Australia is often one of the hottest days of the year for them. And it's the weird thing. I've got a friend that lives there, and they describe how, they have barbecues on the beach in their swimsuits in the middle of winter for Christmas. Very odd, in my opinion. That's just so different from my experience. On the equator, there really are no seasons because it's always getting a lot of direct sunlight. Sure, they may get a slight angling away or towards the sun, depending on what time of year it is, but they still get pretty much 12 hours of sunlight every day, 365 days a year, which means they're permanently hot. Nice diagram here to illustrate this, because again, this is one of those things where students can often get misconceptions. So let's watch this, see if we can break those misconceptions.
You know that Earth orbits the sun, right? And that it takes a full year for our planet to complete its orbit? Earth also rotates like a slightly tilted spinning top. Earth remains tilted in the same direction all year round as we orbit the sun. But that means the sun's light shines differently on Earth at different times of the year. Let's look at Earth when it's winter in the northern hemisphere. Observe how the North Pole tips away from the sun. This means that sunlight strikes the northern hemisphere at a shallow angle for a short period of time. This is why winter weather is generally cool, with short days and long nights. As Earth orbits the sun, we move towards spring in the northern hemisphere. Now Earth is tilted neither toward nor away from the sun, as day and night are about equal in length. As we make our way to the summer months, notice that Earth is still tilted in the same direction, only now on the other side of our orbit. The North Pole is tipping toward the sun. Sunlight strikes the northern hemisphere more directly, and the sun stays in the sky for a longer time. Compared to winter, summer days are warmer, and the sun stays in the sky much longer. Notice, too, that while it's summer in the northern hemisphere, it's winter in the southern hemisphere. Because of Earth's tilt, the seasons are reversed.
So that's an example of how you have these astronomical events influencing our planet's climate and weather and seasonal changes. But then you've also got geographical and geologic features that are temporary in geologic time, because remember, the plates are moving, mountain building and mountain eroding and volcanic eruptions, all of that stuff changes over much shorter geologic periods of time. Climate and weather patterns at Earth's surface. And so we're going to look next at how geography and geology influences climate on these more shorter, sometimes less predictable timescales. So as we've already seen when we looked at the atmosphere, the atmosphere is air, right? It's gases. They are fluids and they move by convection. So that sets up these convection cells, the Hadley, Ferrel, and polar cells that we saw in the previous parts of this unit. They're circular cells. They're like donuts that spin around our planet, and they're just forever happening. As long as we have an atmosphere, and we have an equator. That's what's going to happen. And that's the dominant thing that shapes the climate on our planet. However, the atmosphere is not the only fluid on our planet. We've also got an ocean. We're 75% water, right? We've got so much water on our planet in the oceans, and it's also a fluid. It can also get less dense as it gets warm and more cold, more dense as it gets cold. So it can rise and fall and form convection cells just like the atmosphere does. But the big difference between the atmospheric circulation, which are these predictable, permanent, unchanging convection cells that sit over the Earth's surface. In the ocean, they are not permanent, and they're not perfectly circular, because the ocean is not like our atmosphere where it's uninterrupted. The ocean is interrupted by continents, right? There are land masses that break up all the water. And so you don't get these beautiful circular rising and falling convection cells. What you get instead are currents that get shaped by the wind. Remember, there's always wind blowing back towards the equator. That pushes the ocean around as well. And then those currents hit a continent and get driven along the edge, because they can't go over or under it, obviously. And then you've got north and south, where it's cold and where it's warm. All of those geographical features combine to make this weird convection current. And although the diagram on the right-hand side accurately portrays the warm, red surface currents and the cold, deeper ocean currents underneath, it looks very misleading. It kind of looks like there are many, many different currents, when there really aren't. There are some little temporary currents at the surface. You may have heard of the North Pacific garbage patch, this gyre, which is a little circular surface current. You occasionally get these little surface circular currents going around, but the big conveyor belt is one giant current. So every one of the red and blue arrows that you see there is actually connected into a single system that moves heat from the equator to the poles and back again. Warm water at the surface, cold water at the bottom. Sometimes it hits the continents and up it comes to the surface, or down it goes if it's cold. And so I'm from Scotland, as I already said. Here we are, up on the north tip right there. So we're on the exact same latitude as Alaska over here. Why is it so much warmer in Scotland? And it's always 20 to 30 degrees Fahrenheit warmer in Scotland than it is on the south coast of Alaska. What's going on? Well, look at the ocean currents. Notice where Scotland is, we've got red arrows coming by. That's the Gulf Stream that comes out of the Gulf of Mexico, starting here, winds its way around the tip of Florida, and off it goes across into the North Atlantic, off the coast of Norway. It's carrying warm, moisture-rich atmospheric water, really is what it is, atmospheric water. You've got this warm ocean current, and as the winds blow across it as well, it carries that warm air across northern Europe in this direction. That's where the prevailing winds come. So Europe is always warmer than the equivalent areas in Canada and Alaska over here because of, look at this, notice the blue lines that it gets. These blue currents are cold water. And so Alaska doesn't get the benefit of these warm currents washing past Scotland. So that's an example of geographical and oceanographic features that create these climate patterns that are unique to certain parts of the world. We don't have permafrost in Scotland, but we do in Alaska, and that's because of the interaction between the ocean, the atmosphere, and the land. So for now, you just need to understand that it's all connected, and they love to ask you to make predictions about this in the AP exam. You may have noticed on some of the practice questions that came out from the AP exam, there was one about these ocean breezes that came up, and there's a picture of that down on the bottom right here. Water is a very unusual chemical. It's got a very high specific heat, and as you'll see later on, it actually expands as it freezes rather than shrink, but we'll talk about that later. Oceans are these large bodies of water with a high specific heat, which means it takes a lot of energy from the sun to raise it by 1 degree of Celsius in temperature. So what does that mean? Well, let's imagine it's the peak of summer. And so here we've got, it's A down at the bottom left, we've got this hot land. It's August, you've got hot air rising. But that sunlight has not been able to heat the water as much as it has the land, because the water has got a higher specific heat, a higher heat capacity. It just doesn't heat up the same. So the water is always cooler. That's why we go to the beach in the summer, to cool down in the ocean water, right? But think about what that does in terms of the atmosphere. Where is the hot air? Well, it's not on the ocean, right? It's on the land. So that hot air will rise, and that will pull in air from the ocean where it's cooler, creating what we call a sea breeze. But then the opposite can happen. Where I'm from, down on the close to the Gulf of Mexico stays warm well into October, November, when you may have had already very cold fronts of air coming through on the land. So the land might be very cold and the ocean's warmer. And so now you get this breeze that blows from the land outwards into the ocean where it now rises because it's warmer. So you get these interactions between the ocean, the atmosphere, and the land that sets up these little patterns of wind. And I want to just show you a video that I think is mesmerizing, that shows you these ocean currents to give you an idea of how critical they are at moving heat from the equator all around the planet, and by doing that, creating these weather and climate patterns that affect the whole globe. So look at what you can see here. Here we see these surface currents of just winds blowing. What we're looking at here is the Gulf Stream coming across the North Atlantic. And then notice it goes down. It sinks off the coast of Greenland and Iceland to become a deep water ocean current. You can see underneath here, you can see the topography of the land it's not really land, but it's the ocean floor, right? And so down we go. Here's this deep ocean cold water current, bringing this cold water back again. We may get a glimpse of the mid-Atlantic ridge in a minute. Temporarily, yeah, there it is. There's that zipper down the middle of the Atlantic. You can see when new plates are being formed and new crust is being formed, pushing apart South America away from Africa, but it still has the outline of the jigsaw puzzle where it fitted. Notice this circular pattern going around Antarctica as well. We've got surface cold currents that go down again. If you remember on Nemo, if you ever saw Finding Nemo, there was that current off the coast of Australia that they all got, the turtles got stuck in, right? And they got shot along the deep ocean. There's another current, you can see it right there. So this is going all over the planet, and it is just shifting the hot water from the equator around to the poles. Okay. Ocean currents interact with land, so does the atmosphere. And so those big currents, as long as the continents are located where they are right now, we'll continue to see those ocean currents performing that same function in the same way, setting up these dominant climate patterns. But you also get much more local things happening as well. Think about if you've ever had the opportunity to climb a mountain, it gets colder and colder as you go higher and higher in the troposphere. But then think about what that does to the humidity as well. The colder it gets, the less able that air is able to hold on to the water vapor, and then ultimately it'll condense. And so you get rainfall happening at the top of the mountain where there may not be any down below. And so altitude influences rainfall and precipitation and temperature, of course. So does latitude, right, which is 0 degrees at the equator, and then you go 30, 60, 90 degrees at the poles. Latitude influences it because of the amount of sunlight that you're getting, because of the tilt of our axis. Ocean currents, as we just saw, they can also shape the climate of patterns, making Scotland far warmer than Alaska. And then we saw about proximity to large bodies of water. Water has this moderating effect on land temperatures because of its heat capacity. And there's also albedo. Now, we're not really going to talk about that here, but some surfaces are highly reflective, and so they don't warm up very much. Think about if you're walking to your neighborhood pool in the middle of August and you live somewhere very hot, would you rather walk on the black top road or on the white concrete, which is going to be hotter? The black surface, right? You walk on the concrete, or even better, on the grass. And that's to do with albedo, which is this reflectance. So ice and pale, shiny surfaces, they reflect sunlight, so it doesn't turn into heat at the surface. So think about all the different kinds of surfaces there are on the planet. Think about glaciers and ice caps and how reflective they are. If they're gone, what will that do to the surface? Well, it'll cause them to heat up more, right? Which will change the circulation of the atmosphere. It'll change those convection patterns, change the wind currents, which will change where it's raining and where it's not. Think about a forest compared to a concrete city and the difference in the heat between those two. So geographical features and man-made features can have a big influence. And one of the really big influences that we see, and especially in North America, is what we call the rain shadow effect. And this is a geographical feature that happens where you have a mountain chain. So we've got a very large mountain chain in North America. We've got the Rockies. We've also got the Cascade Mountains that are off of that subduction zone off the Pacific Northwest. Remember, our weather, if you think about where the frontal systems come from throughout the year, they typically come from the northwest, up in the kind of Washington, Alaska, and Portland area, and they blow across down towards the southeast. Think about those cold fronts that come through during the fall, the spring, and the winter. That's where they're coming from. So that is an air packet that's coming from the Pacific Ocean, where it's picked up large amounts of water and moisture. And then across it comes, and then it hits the Cascade Mountains, and it hits the Rocky Mountains. And what does it do? Well, look at the diagram in the bottom right here. That moist air gets forced upwards over the mountain range. If it was just a single mountain, then the air would just kind of flow around it like a rock in the middle of a river. But when there's a barrier, like a mountain chain, well, now it can't really go around it. It's got to go up and over. And so as it goes up in the troposphere, the temperature decreases, and so it gets colder and colder. And at some point, it'll be cold enough for all of that water vapor from the Pacific Ocean to condense, go into clouds, and then as the clouds get forced up over the mountains, they will drop all of their moisture. And then the air keeps flowing, right? The wind keeps blowing across the mountains. But look at what happens on the right-hand side of the mountain. Now the air that's flowing in from the Pacific, it's lost all of its moisture. It has dumped it all as precipitation on what we call the windward side of the mountain. But the windward side is wet. So use that alliteration to remember this. Windward is wet. And then notice on the other side of the mountain, this what we call the leeward side, there's less moisture. The windward is wet, leeward is less. And so the leeward side of the mountain, you can see it's very dry. So think about the biome that you might find on the windward side of a mountain. If it's on a tropical place, you might even get tropical rainforests on this mountain. You certainly get forests and lush vegetation. Whereas on the leeward side, where there's less moisture, what are you going to get? You're going to get those drier kind of Mediterranean chaparral type environments if it's warm enough, when you may get some kind of dry grassland or even deserts you can get. If it's a strong enough rain shadow effect, then you get deserts on the leeward side. And that's why we call it the rain shadow, right? Because we're on the shadow side. If you imagine the rain coming in, see the diagram of the rainfall angling in there on the windward side of the mountain, or the eastern side, the right side of that mountain is on the shadow side, where the mountain has cast a rain shadow, where there's no rainfall. So those two things have a big impact. And then the very last thing in Unit 9, Unit 4 is Unit 4.9. And this is a complex concept to understand. A lot of students struggle with this, and they love to ask about this, especially on multiple choice questions in the AP exam. We have not seen, really, certainly not recently, an El Nino free response question. But I think it's definitely fair game moving forwards, because it is an environmental problem for some when these events happen that has atmospheric and oceanographic and land-based effects, which also has ecological effects on biodiversity, both on land and in the water, and it has economic consequences. So it's one of these wonderful, multifaceted, interconnected concepts that really is fair game on the AP exam, because it's so interconnected. The College Board could ask you anything they want about those connections. So let's get a look at it and make sure you understand it, and we'll finish this whole lecture. I know it's been real long. Hopefully you have chunked it up and not just sat and listened to the whole thing. Let's look at El Niño and La Niña. So these two things form part of a climatic oscillation. And when something oscillates, it means it varies and flips between two alternating states. That's an oscillation. It goes from A to B to A to B to A to B. That's what we mean by oscillate. And so the El Niño Southern Oscillation, or ENSO as it's often called, is a regular cyclical climate oscillation. It's triggered by changes in the atmosphere, but it has impacts not only in the atmosphere, but on the ocean and on the land. So first of all, let's just look at what's happening when there is not an El Niño or La Niña event. We call that normal conditions, and that is what is shown over here on the right-hand side by the top right. This is normal conditions on the top right. So you're seeing three things here. First of all, notice where this is happening. It is in the Pacific Ocean. You can see, central and some of the southern states of North America over there. You can see Papua New Guinea, a little bit of Australia, Indonesia over on the right, on the left-hand side. So what normally happens? Well, remember the diagram that we saw of the air patterns, the wind patterns blowing towards the equator, and that they are curved. Notice those wind patterns, whether they're coming from north of the equator or the south, they curve as they hit the equator, and they blow from the Americas over to Indonesia. So you've got this warm wind blowing across the ocean surface towards Australia, and it's unbroken, right? There's nothing out there. There's Hawaii and a couple of little small islands, but that wind is a strong wind that just blows the warm air towards Indonesia. But it's not just warm air that gets blown in that direction. It's also making waves, right? It's blowing the surface water at the equator. So that surface water at the equator is already very, very warm. And you have these trade winds, these dominant normal condition winds blowing from South America to Indonesia, pushing the warm water over towards that direction. And you can see this gathering, what we call a warm water pool, this piling up of warm water over on that side, the western edge of the Pacific. What does that do? Well, that creates warm rising air in the area where we've got the warm ocean. Yeah, we've learned about these convection currents. So up rises the water, as it rises, up rises the atmosphere, the hot, moist air, and as it gets higher in the troposphere, it gets colder, and it dumps all of its moisture. So the normal atmospheric conditions over both sides of the Pacific are, over on the western edge, where you've got Indonesia, Australasia, you have moist conditions. You've got high rainfall, it's muggy, it's humid, it's hot and wet. Got hot water all around those island chains. But over on the eastern side of the Pacific, where we've got the Americas, look at what's happening. Here we've got descending dry air. So that creates these typically fairly dry conditions over here in Central and South America on that western coast of Central and South America, which is the eastern side of the Pacific. You've got high pressure, dry descending air. But now look at what's happening in the ocean. You see this angle is formed. What the line is called a thermocline, where above the line, I wish it wasn't blue and was more kind of a more reddy color, you've got warmer water above the line. But remember, the wind is blowing in this direction. It's blowing all the surface water across to where it can pile up over here. And so the arrows of the wind's blowing the water this direction towards Australia. Does that mean that the tide just keeps going out in South America? Well, no, just like you don't suffocate at the equator because the air that's rising is replaced by air coming in. The same thing happens with the fluid ocean, where the warm surface water, it is getting blown away from South America here in this direction, but look at what that does. It pulls up cold, deep water from deep, deep below in the Pacific Ocean. We call that upwelling, and that upwelling is really, really important for the biodiversity and the fisheries of Central and South America on that Pacific coastline. Because the cold water, as you'll learn later on in your water pollution unit, it contains more oxygen, which can often support a wider diversity of organisms, but even more importantly, all of the nutrients that have sunk to the bottom of the ocean and would be unavailable at the surface because they're gone. Well, now this upwelling brings those nutrients up to the surface where they can feed those aquatic ecosystems, the algae. Think about the kelp forest that exists all the way along those coastlines, even way up into the northwest coast of Northern California, and on into Oregon and Washington. You get kelp forests, and that's what's feeding those kelp forests. It's this nutrient-rich cold water that's coming up. So that's normal conditions. Prevailing winds blow across the Pacific from the Americas over to Indonesia, pushing the warm surface water over westwards in that direction, creating in the atmosphere warm, wet weather conditions, so lots of rain over in Indonesia, but drier, cooler conditions in Central and South America. But then in the ocean, the pushing of all the warm surface water pulls up cold, deep water containing nutrients. We call that upwelling. So that's normal. That is what is going on in typical conditions most of the time in the Pacific. But then, every 2 to 7 years or so it's a pretty big range here, you get this cycle, this oscillation starts to happen, where we enter something called an El Nino year, or an El Nino system. So look at the diagram on the bottom right. This shows you the El Nino conditions. Notice what's changed in the atmosphere. Really what's happened here is that the winds, the trade winds that normally would be blowing all the way from the Americas over to Indonesia, have weakened or kind of stopped. And now you've just got hot air just rising all along the equator, all over the ocean and Pacific. What does that do? Well, that means it shifts the zone of all the rainfall. See what's happened here? It's moved further back along the Pacific. And actually, in a really bad El Nino year, not only do those winds that normally blow across the Pacific weaken, but they can even reverse. And you can end up with all of that rainfall and cloud being pushed even further back this way, because now the wind's blowing the opposite way. And so you get incredible catastrophic flooding and rainfall and things happening over the coasts of Central and South America. So you get a climatic change during an El Nino. It gets wetter over there. Notice though, as it gets wetter over in the Americas, it's getting correspondingly drier over in Indonesia and Australasia. But look at what's happened in the ocean. Look at the thermocline. Look at what's happened to the upwelling. There isn't any. All of that upwelling that used to bring the cold nutrient water, if you look up on the top diagram, up here, bringing all these nutrients up to the surface. Well, now, it doesn't happen. It's just stuck. There's no upwelling at all. So what does that do? Well, it means all the nutrients that used to feed all those ecosystems, the nutrients are reduced now. All of that extra oxygen, the colder water maybe that would have been there, that the water could hold, is gone now as well. So you get fish that migrate out of there, and that leads to a collapse in the fisheries often, those coastal communities in South and Central America. There's just less fish there, and that has other impacts on the biodiversity as well. So an El Nino is a change. Now, it doesn't necessarily mean it's bad. It's just that's part of the cycle, right? You get a change in the atmospheric and oceanic circulation every 2 to 7 years that changes the atmospheric situations on land in terms of rainfall, and it changes biodiversity in the ocean. Now, sometimes you get a third thing that happens as part of this oscillation. You don't just get an A and a B and an A and a B and an A and a B. Sometimes you get an A, B, A, C, A, B, A, C. And that C is called La Niña. So let's just get a quick look at La Niña. Notice it's very similar. I'm going to go back to normal conditions. You've got strong winds blowing across the Pacific, creating this rising moisture and upwelling. Look at La Niña. It's essentially the same thing, but even stronger. This is extreme normal. Look, notice, whereas the rainfall used to be kind of right about here above the Pacific, put even further, way deep into Australia now and Papua New Guinea, and that can lead to catastrophic flooding, monsoon conditions over in those areas. But you also get this weird situation here. Look at what's happened with these winds. You get this unusual conditions where you can even get extra rainfall happening over there. I don't think they're likely to ask you very much about La Niña, because it is kind of confusing. But just know it's part of this cycle where you can get normal, El Nino, normal, extreme normal, normal, El Nino, normal, normal, El Nino. It kind of cycles around. And again, it's every 2 to 7 years where you get these cases of extreme normal, El Nino, normal. That's the cycle. The primary differences are between the normal cycle and the El Nino cycle of the oscillation. Those are the two you should look at. And to help you understand it, because it's hard to see it in diagram form, there's a wonderful video which will be the end of this particular presentation. Let's just watch this video that I think does a masterful job of explaining what is going on during El Nino and La Niña.
Warmer or colder than average ocean temperatures in one part of the world can influence weather around the globe. Boggles the mind, right? Here's how it works. During normal conditions, trade winds, which blow from east to west, push warm surface waters towards Asia, piling it up in the western Pacific. In some years, though, the trade winds weaken. The warm surface water moves eastward and reduces upwelling of cold water off the coast of South America. Climatologists call this El Niño. Its climate impacts show up mostly in the wintertime over North America. The warmer ocean fuels an intensification and southward shift of the jet stream. This brings flooding to the southern United States and warmer, drier conditions over parts of the Pacific Northwest, northern U.S., and Canada. But eventually, those trade winds pick up again and sometimes become even stronger than normal. When that happens, they blow the warm water back into the western Pacific and restart the upwelling of cool water towards the surface in the eastern Pacific. These strong trade winds are a signature of what is called La Niña, unusually cold conditions in the tropical Pacific that displace the jet stream northward. La Niña can lead to drought in the southern U.S. and cooler temperatures, heavy rains, and flooding in the Pacific Northwest. El Niño and La Niña together are part of a cycle that influences extreme weather and can impact food production, water supply, and even human health, not just in the U.S., but in many parts of the globe.
So there you go. Hopefully that has given you a good insight into El Niño, La Niña, and how they affect life on Earth, especially around the Pacific. So this whole unit, in summary, is really about learning the foundations of the physical systems that connect all of the others, right? So you've got the biosphere, you've got the lithosphere or geosphere, you've got the atmosphere, you've got the hydrosphere, where you've got things happening in the ocean, in the atmosphere, and on land that all interact together. So yes, you do need to learn the individual pieces of that, but the way you'll be asked about them on the AP exam is by connecting them together and thinking about the impacts of one on the other. That's really the way the AP exam is written. So hopefully that was something that was enjoyable to you. It was a long presentation. Hopefully you've seen it in little chunks. But that's the end of Unit 4. And remember, you are going to build on this unit throughout the entire rest of your course. Good luck.